Let's now look at how to do triple integrals using cylindrical and spherical coordinates. We'll do cylindrical coordinates first. Remember the cylindrical coordinates are r, theta, and z, and x, y, and z are given by x is r cosine theta, y is r sine theta, and z equals z. Now something important to remember is that when we're integrating over solids, we're going to be using all three of the cylindrical coordinates. So our integrals are going to be of the form dr, d theta, dz in some order. Now, an important thing to wonder, though, is what is the volume element in cylindrical coordinates? It's going to be something dr, d theta, dz. But we have to figure out what goes in this spot. Just like what happened when we changed coordinates in 2 dimensions, what goes here is a Jacobian determinant. So let's calculate the Jacobian determinant for cylindrical coordinates. And then whatever we get, we're going to memorize so that we don't have to do this over and over. So the Jacobian for cylindrical coordinates will be the matrix made up of dx dr, dx d theta, and dx dz, dy dr, dy d theta, and dy dz, and dz dr, dz d theta, and dz dz. So just like it did for functions of 2 variables, this Jacobian determinant is going to measure how much volumes are magnified when you switch from one coordinate system to the other. So let's calculate all these partial derivatives. Let's start off with x. The derivative of x with respect to r is cosine theta. The derivative of x with respect to theta is negative r sine theta. And the derivative of x with respect to z is 0. Moving down, the derivative of y with respect to r is sine theta. The derivative of y with respect to theta is r cosine theta. And the derivative of r with respect to z is 0. And finally, the derivative of z with respect to r is 0. The derivative with respect to y is 0. And the derivative with respect to z is 1. So if we take the determinant of this matrix, we're going to get cosine theta times r cosine theta minus 0 minus a negative r sine theta times sine theta minus 0 plus 0, which is r cosine theta squared plus r sine squared theta, which is r. Now, actually, I wasn't quite careful over here. dv is actually the magnitude of the Jacobian determinant times dr d theta dz. But we're going to be careful so that we set up our bounds keeping r positive. So the absolute value of r will be r. So in cylindrical coordinates, dv is always equal to r dr d theta dz. And I would suggest that you memorize this substitution for cylindrical coordinates. And then if you want to switch from rectangular to cylindrical, all you have to do is substitute these values in for x, y, and z, and replace dv with r dr d theta dz.